So good afternoon. I would like to welcome you to the 27th annual Dr. Shih-I Distinguished Lecture. My name is Konstantina Trivisa, and I'm the director of the Institute for Physical Science and Technology. Please have in mind that this webinar is being recorded and will be available on YouTube after today's lecture. The last 30 minutes of today's event is reserved for a Q&A discussion session with Dr. Huy Cow and panelists. We invite you to submit questions throughout the webinar using the Q&A function located at the bottom of your screen, and we will answer as many questions as we can at the completion of the lecture. Let me say a few words about the person that we honor today. The Dr. Shih-I Distinguished Lecture Series honors the memory and many contributions of Dr. Shih-I, who served on the faculty at the University of Maryland for about 35 years and was a founding member of the Institute for Fluid Dynamics and Applied Mathematics, now known as the Institute for Physical Science and Technology. Professor Pai was a pioneer in the field of aerodynamics, helping to advance that field from its infancy to its current level of sophistication. His breakthrough discoveries about the effects of structure on turbulent flow led the foundations for engineers to move from low-speed aerodynamics through high subsonic and on the supersonic and hypersonic speeds. Among his many awards and honors are the Alexander von Humboldt Foundation Prize, the Guggenheim Fellowship, an honorary degree from the Technical University in Vienna, and many others. Dr. Pai was named an honorary research professor at the Institute for Physics, Academia Sinica, China, and received the Centennial Medal from the A.J. Clark School of Engineering here at UMD. Dr. Shih-I was born in Anhui province in China. After graduating from the National Central University in Nanjing, he moved to the US and received his master's degree from MIT and then a doctoral degree in aeronautics and applied mathematics from Caltech. Over his career, he authored 14 books and about 200 articles. Some years ago, Dr. Pai's children established the Dr. Shih-I Lecture Series at the University of Maryland. Today, October 19th, 2021, marks the day of the 27th annual lecture. We have here with us today the Honorable Shu-Pai Yang and Dr. Chang S. Yang. And without any further ado, I would like to introduce our distinguished speaker. So it is my great honor to introduce our distinguished speaker, Dr. Huy Cow from Yale University. Huy Cow is the John C. Malone Professor of Applied Physics and Professor of Physics and Electrical Engineering at Yale University. Huy Cow began her career at Northwestern University in 1997 before accepting a position at Yale in 2008. Dr. Cow's research interests and activities are in the areas of mesoscopic physics, complex photonic materials and devices, nanophotonics, and biophotonics. She has conducted experimental studies on unconventional lasers, including random lasers and chaotic microcavity lasers, and found their application in speckle-free imaging, multimodality microscopy, and parallel random number generation. In addition to fundamental studies on complex, chaotic, and disordered systems, she has harnessed a disorder for photonic device applications. I should mention here that she invented a complex spectrometer based on a disordered photonic chip. Huy Cow is an elected member of the National Academy of Science and the American Academy of Art and Science, and she's a fellow of the American Association for the Advancement of Science. She is the recipient of numerous awards and honors, including the Maria Geoberg Mayer Award, the Friedrich Wilhelm Bessel Research Award by the Alexander von Humboldt Foundation, and the Outstanding Young Researcher award by the Overseas Chinese Physics Association. Later this evening, she will receive the IEEE Photonic Society Aaron Grenzel Award for groundbreaking contributions to experimental studies on non-conventional laser and for pioneering their applications in biomedical imaging, projection, and cryptography. Huy Cow received her bachelor's in physics from Peking University in 1990, her master's degree from Princeton in 1992, and her PhD from Stanford in 1997. Her lecture today is entitled Structural, Color Origin, and Evolution in Nature. Huy, the floor is yours. Thank you for being here.
Thank you very much for this kind introduction. Let me try share my screen. Okay. All right, I hope you can see my screen now. Right, okay, good. So first I would say it's really a great honor for me to give this 27th Shih-I Pi lecture. I have actually read the legend of Dr. Pi, and I think this is really inspiring for all of us. So today I will try to talk about the structural color in nature, how they, where they come from and how do they evolve. But before I start, I'll maybe say a few words about myself, because very often people will ask me some questions. The first question they ask me is, why you study physics? The answer is simple and straightforward. My father was a professor of physics. So I just followed his footsteps, and I even did my bachelor's thesis with my father at Peking University. Then the next question, people ask me very often say, why you choose to study, optics, which is the physics about light, right? And this actually, the answer is, simple, but may not be as straightforward. So when I was about 5 years old, my father asked me this question: what travels farthest and furthest in the universe? And I don't know. I would say, oh, maybe car, or airplane or train. My father said, no. What is travel farthest and furthest is actually light. Nothing can travel faster than light. And I was very intrigued. I would say, wow, light is very special. I would like to study light to understand why light is so special. So now, after studying light for many years, I indeed, realized light, it is special. And we all experience the power of light. The very fact that I can give this, lecture, remotely is really due to this telecommunication by optical fibers, right? And also, like when we're using cell phone or TV or computer, we really they are really mostly come from this kind of major advances in studies of optics. So these days, for example, light emitting diodes has been used for like lighting, and the solar cell has been used to provide clean energy. So we see, the application of lights everywhere in our daily life. So I think that's a very exciting field, optics, and also it's a very, interdisciplinary field. And as an optical physicist, I was always fascinated by this, the brilliant color that are generated in nature. So here shows a few examples of the, like some birds. You can see all the vivid color they, generated. And I was wondering, how they are generated, what are they used for? So after I moved to Yale University, I finally had a chance to study the color in nature, thanks to this interdisciplinary collaborations at Yale, and also thanks to this vast collection of samples at the Yale Peabody Museum. So before I talk about, the color in nature, let me first just briefly introduce, how color is generated in general. So there are several ways of producing color. One way we call the chemical color, that is produced by pigments. So let's consider we have a white light. The white light contains all colors. And then we have, like a dye that will have wavelength dependent absorption. For example, if we want to paint on the white paper, when we put a blue dye, what happens is that when the white light hit the blue dye, the red and the green color will be absorbed by the dye, and the blue will go through, and then it will be reflected by this white paper and then comes back. That's why we see blue. Okay, so that is basically the color is determined by the pigments, the wavelength dependent absorption of light by the dye molecules. So this is one way to generate a color. And another way is actually to generate color by structure. So we call it physical color. Here is one example of these birds. You see these blue feathers. That's actually generated by structure color. So what is the structure color? Basically, we try to using this kind of nanostructures to have wavelength dependent reflection of light. Meaning that, for example, here for this kind of structure, when the white light incident onto it, only the blue light is reflected, and the green and the red will be transmitted, and then it will be absorbed by a black base. So that's why we see this blue color. So this color is actually generated by the structure, so it is also called structure color. And structure color has been used a lot in nature by different animal species. And the questions we try to answer is, how the structure color is produced in nature, and what is the function of the structure color? How structure color has been evolved in nature, and what can we learn from nature? So to answer those questions, of course, we cannot do it for, a person just in one, discipline or in one department. Actually, we have an interdisciplinary research team at Yale to answer these questions. It contains, people all the way from evolution biology, molecular biology and biochemistry, soft matter physics, and optical physics. So all the people have to work together to really, understand this structure color in nature. So there's several ways the color can be generated by structure. The most, simple way or maybe common way to do it is so-called light scattering. For example, if you have some small particles, they can scatter light. And if the particle size is much smaller than wavelength, then the scattering strength is inversely proportional to the wavelength. Sorry, is inversely proportional to the wavelength, meaning that the shorter the wavelength, the stronger the scattering is. That's why the blue sky we have seen. That's because in air there's some small particles. They scatter the sunlight, and the blue light is scattered the most. That's why we see the blue sky. So that is a very easy way to generate structure color, by just particle scattering of light. Another way to do it is by this using the thin film interference. For example, we see this soap bubble, right? This bubble has to have this thin layer of soap, right? And we can see the color when the white light reflected from it. This actually comes from that when the light hit on this thin film of soap, it can be reflected from the top surface and also partially from the bottom surface. And those reflected light will interfere with each other. And only at a certain wavelength, the interference will be constructive, meaning those fields will add together to make a stronger reflected light. That's why we see the color. But for other wavelengths, they will not interfere constructively in the reflection, so they are mostly transmitted. That's why we can see the color from this thin film interference. Another way is to using the so-called multi-layer interference. The multi-layer interference is that we can have two different materials, A and B, And they actually forming this thin layers, and then the alternating layer A, layer B, layer A, layer B. So they form a periodic structure. And then when the light comes in, it will reflect it from multiple interfaces here. And all this reflected light will interfere with each other. Again, at a certain wavelength, they will interfere constructively. That will make the color for the reflected light. So by changing the period of this structure, actually we can changing the color of the light being reflected. So this has been used, widely in nature to generate the color. Here shows one example of this bird. That's actually you see this kind of a structure here, and that is a structure, this kind of periodic structure in one dimension to generate the color. In addition to one-dimensional structure, in nature there also have been two-dimensional periodic structures, produced, or even three-dimensional periodic structures. Okay, and those structures, again, they can scatter light, and then for certain light, they will interfere to produce the color. So this, as I said, has been widely used to generate the color in nature. Now, one thing for this, not only by birds, but also by butterflies. So here show the butterfly, the colors, that's also generated by this kind of periodic structures. And because the period is different from different angles, so the color is iridescent, right? So for example, we can see this color, you see that you're going to see different color when you try to view it from different angles. The reason is because, as I said, this periodic structures, the period will be different in different directions. So in different directions, there will be different, light will be, reflected and interfere constructively. So that's why we call this an iridescent color. But in nature, we also see this non-iridescent color. For example, if we see those birds, you can see the blue feathers. They actually look blue in all angles, not like the butterfly, right? You can see the feathers on the chest or on the shoulders. They all look, blue. And we also measured the reflection spectrum from a single feather. Then we can see that here you can see the horizontal axis, it is a wavelength. Vertical axis is a rotation of the feather. And then the red color shows the reflection peak. So we can see that this reflection, will maximize at a certain wavelength. And this wavelength does not seem to change with the viewing angle. So we call this non-iridescent color or isotropic color. The color looks the same in all angles. So now the question is how this color is generated. More than a century ago, people think this blue color of this bird feather is generated by Rayleigh scattering. That is a single particle scattering, just like the blue sky. And actually, a very well-known Indian physicist, Raman, who actually got Nobel Prize for the Raman scattering, he studied a common blue birds in India called Indian roller. And then when he studied the color of this, bird feather, he realized that this does not seem to be single particle scattering like a Rayleigh scattering. Seems there's some interference effect in there. So we know that the interference effect usually generated by this kind of periodic structures. So, but he cannot see the color producing structure with optical microscope. At that time, there's only optical microscope. The resolution is not sufficient to see those kind of very small, scale color producing structures. So this is his speculation. And then later on, people have invented the electron microscope, which has much better spatial resolution than electron microscope. Then when people try to see the, this kind of color producing nanostructures in the bird feathers, this is what they see. For example, here, we see that this white, it is air, and the dark, it is a protein called beta carotene. So there's this two different types. On the right here, we call it a sphere type, which means we see these spherical air cavities buried in the protein beta carotene. And on the left, we call the channel type, It's like this kind of elongated twist air, tubes buried in this protein, right? So when people saw this, people say, well, we don't see any periodicity. It looks like random here. So then there cannot be an interference effect because they should be washed out in a random structure. So people think, Raman was wrong. This actually is coming from maybe single particle scattering, like the blue sky people thought previously. Then after half a century later, actually my biologists, including my colleague, Professor Rick Prum at Yale University, they actually showed Raman was right after all. So how he knew Raman was right? Because he tried to do the spatial Fourier transform of this kind of structures, taken by the electron microscope. And then he realized the structure is not completely random. There are some order in there. So later on, they did this so-called X-ray scattering. X-ray scattering, is more like doing the, physical Fourier transform of a structure. So here you can see this pattern here, and we see a ring. Part of the ring is blocked by this beam block. So, but it is a ring, so it is isotropic. So this ring tells us there is a dominant spatial frequency in this structure. That dominant spatial frequency corresponding to the radius of this ring. And because this, dominant spatial frequency is really, same in all angles, the structure is isotropic. So that's why they produce this isotropic color. But this color is still coming from the underlying order in this structure that leads to the interference effect. So now let's try to see how that the dominant spatial frequency will determine the color of reflection. So let's consider we have the light coming in with a wave vector k coming in. Then then it will be scattered, by the structure once, and then it's going back. So in the backward direction, we have another k out. So this, and their difference between k in and k out is equal to the spatial vector of the structure. And because we consider elastic scattering, meaning the k in and k out has the same amplitude, that will tell us that the spatial frequency q will determine the wavelength of light that can be reflected back, through this construct interference effect. So that is basically determined in the backward direction what we see. Because this dominant frequency is the same in all angles, so no matter in which angle we see this bird's feather, the back coming back to us, the color is look the same, because that's because the spatial frequency is the same in all angles. But how about scatter into other angles, not in backward direction? Say I have a light coming in this way, and then the light will be scattered in another direction, which is characterized by the angle theta. So now this, the difference between k in and k out here still has to be provided by the spatial vector of the structure. And this will determine what is the wavelength of the light can be scattered into a particular angle theta through the construct interference. So with a simple math here, we can see that actually the wavelengths for different scattering angle will be different, even we have the same dominant spatial frequency. So this is because we are trying to illuminate at one angle and then try to observe from a different angle. This is actually how Raman realized the color of this blue feather is actually coming from interference. So we also did a similar experiments. So we have a single feather barb. We illuminated by white light, and then we try to measure the reflected light, the spectrum as a function of the scattering angle. So again, here shows this, horizontal axis, it is a wavelength. Vertical axis, it is the angle of this observation, theta. And the red color shows the reflection peak. The peak, you can see that is actually changed slightly with the angle. You see that? That's because, we fix the input, we try to see the light from different angles. If you always see from the back, it is the same, color. But this very tiny shift, is fairly small. That is what Raman noticed. That's why he thinks this is must coming from interference effect. So if from this peak position of this reflection, and also from the angle, we can recover what is the spatial frequency of the structure. And we find it is the same in all angles. That means this structure, it is isotropic, but has some dominant spatial frequency that determine the color of the reflected light. So that is actually what we learned. Then we say, let's try to just confirm this by place the optical reflection spectrum on top of the X-ray scattering peak. Then we see they really match pretty well here. So that is confirmed. This optical reflection peak is coming from this structure, has some particular spatial frequencies. That's give us from the small angle X-ray scattering. So this looks great for the channel type on the left, but for sphere type, when we try to put them on top of each other, we see the optical reflection spectrum, the main peak is really matched well with the X-ray scattering peak. But we see there's a shoulder, which is here. And where does that coming from? That coming from actually double scattering. That means that the light will be scattered twice by the structure. The first time from the wave vector K in to intermediate K vector Km, and then scattered again from Km to the final K vector K out. Let's consider in the backward direction here. So now we know all this K vector should have the same magnitude because we consider elastic scattering. And from a simple math here, we can see that again, the dominant spatial frequency Q will determine the wavelength for double scattering. And this wavelength is different from single scattering. So that's why we see a secondary, like a peak or shoulders from this optical reflection spectrum that's coming from this double scattering. But again, this scattering is coming from the dominant spatial frequency or like the periodicity in the structure. So now we say, okay, now we understand how this color is kind of generated by this bird feather, this isotropic color. They basically using this kind of structures. If you see here, this structure is not completely random. You can see some short range order even if you look for a long time, because all the air cavities, the spheres, they're almost the same size. And locally, if you see locally, they kind of have a similar spacing, right? So that means they have some short range order, and this kind of order allow them to pick up the the wavelengths to have constructive interference in reflection to give us the color, right? But the question is, they don't want have a long range order, because if you have a long range order, then the period will be different in different angles, and that will make a iridescent color, angle dependent color. So to make an angle independent color, they cannot have a long range order, so they have only short range order. But the long range, you see, there's no order here. This allows them to have this isotropic structures to give you, this kind of isotropic color. So pretty smart design. We say, okay, now we understand what's going on. Now let's try to, mimic it to generate this. So what we try is that we say, okay, now let's try to, using, this is in collaboration with Professor Eric Dufresne's group, is that we're using two different sizes of polystyrene spheres. It's like a glass, very small spheres, about 200 nanometer in diameter. And then we mix those two different sizes of polystyrene spheres in solution. Then we spin coat it on a glass substrate. Then we can see this kind of really a blue, color from this film, right? The reason we're using two different sizes is because that, if we're using a single size, then they can, assemble to a periodic structure that will give you iridescent color. If we don't want long range order, we only have short range order, we have to, using two different sizes, so to, suppress the long range order. So that's why we can try to using this to give us isotropic color. Indeed, if you see these films, if we see from normal direction or from a 30-degree angle, clearly we can see it's the same color here. And to confirm this, we actually did X-ray scattering experiments, and clearly we can see there's an isotropic ring. That means there's a dominant spatial, frequency or period in this kind of structures, in these thin films, and they actually, pick up this blue color to, reflect in all angles. So we say, okay, that's great. Maybe we can using this to get a very large scale, like a paint, right? To really paint using this kind of structures. It's pretty easy to make. But if we want to paint a wall, we cannot do spin coating. So what we typically do, we basically try to do this called a drop casting, right? So we have this solution, we drop it on the substrate and then let it dry. So after that, we only see the blue color, around the boundaries where the film is relatively thin, like in the previous case. In the center, the film is rather thick. Now we see a white, it's a white color. And what happens here is that, if the film is very thick, then actually, if we see in the central part, when we see the reflection spectrum, it's pretty much a high reflection for all wavelengths. That's why you look white, because any color will be reflected. The reason is because, indeed, as we said, the short range order will make the blue color reflected first, right? Because it's enhanced the reflection of the blue ones. But if the sample is too thick, the red color or other color, they can still be scattered, but maybe have to travel a longer distance before they can be reflected back. So if the sample is thick enough, at the end, all the color can be reflected back. Maybe blue will start first, but all others can be reflected. So that means we cannot get this kind of color. So then we say, how did bird do it? Okay, so now we go back to see again, this is a bird feather. So here shows like a low magnification cross section of a feather barb. It's like a cross section. So this outside it is a skin, and then the color producing structure is right underneath the skin. You can see that they are not very thick. It's about 10 micron. And then after that we see this kind of a melanin, which is like a black pigment to absorbing all colors. So what happened is that when the light incident through the skin to the color producing structures, which has only short range order, the blue will be reflected, right? But the red, because the structure is not so thick, the red does not have a chance to be reflected yet. Then it will going through the structure, then being absorbed by this black pigment melanin. So that's how the color is generated. So now we say, okay, now we learn from birds. Let's do that too. We have this, I used to tell you, we have this solution of two different size of polystyrene spheres. Now we're adding some, carbon black. It's like this carbon black nanoparticles just from the ink, right? You just when we put some ink in there. And those carbon black nanoparticles it has a broadband absorption, so they can absorb in all colors. So we gradually increase the concentration of the carbon black, nanoparticles, and then do the drop casting. So now you see that when the concentration is, higher, we start to see the color comes up, right? We initially have a, white. Then for the same thickness, we can start to see the green-blue color appears. So what happens here is that initially, as I said, all the colors can be reflected because the sample is thick. But later on, because there's just a carbon, so they are going to absorbing, light. For the blue light, they'll be quickly reflected because their reflection is enhanced. So that's why you can still coming out. But for the red color, they have to go a longer distance before they can be reflected. But before they're being reflected, they have been absorbed. So that's why we can see this kind of reflection peak in this kind of optic spectrum here. So that means that if we add black into white, so we mix black and white, carbon black with this paint, what we got? We don't get gray, we get color, like this kind of green-blue color. So that's coming from this interplay between absorption and light scattering. So this kind of structural color, one advantage is that it can last for a very, very long time. So here shows some like I think this is a 40 million years old fossil of beetle. You can still see color now, right? And of course, this color is different because the material is changed. It is, falsified. But we can, people can try to recover from this kind of structure. They can recover what would be color 40 million years ago. But in any case, this basically say that if we're using this for paint, the paint will never fade, right? And also this will be very useful to like say for clothes or for cosmetic, because this color is generated by structure, not by pigments. So we can select the material that is like non-toxic and environmental friendly. So we can using those materials, and then by tuning the nanostructures, we can make this kind of structure color, right? We can also actually doing that to paint a car. So this basically showing that this kind of structure color can have a lot of applications in coating, in cosmetics, and also in textiles. But now let's go back to the color in nature, right? So we see this kind of structure color in nature, but now the next question is how this color producing nanostructures are created in nature, right? And how the structure color evolved in nature. So let me try to first answer the first question. Let's go back to the blue feather, here again. So I showed you we have these two structures. They are not completely ordered, but they are not completely disordered. So we call it a quasi-ordered structure, right? So there's this kind of two type. And the question is how they are generated, how they are produced, how they created by the birds. And to do this, my colleague, Professor Rick Broom, have studied this with acrytophan. So they look at this blue feather from a parrot. So here shows a schematic. So this feather has the rachis, and then there's a barbs growing from it, okay? So when you see this barbs, they actually, near the base, there's no color. Only near the tip, there is color. So the near the base, it's a newest material because it's grown from it. On the tip, it is oldest material, right? But the oldest one we see the color, the newest one we don't see it. So how color is created during this kind of evolution? During this growth. So here shows the electron microscope image near the base. That is we call regime 1. So in regime 1, you see that the cell. So this basically showing the cell is still alive. So you see that they are mixed, with the water. So everything, there's a lot of water in there. So that's why we don't see any structure to produce color. As they grow away from the rachis, they are getting less nutrition. Then they got sealed off. So the cells start dying. During this process, they are going to form this kind of a large air cavities, and the proteins become concentrated in some regime. Eventually, in those very concentrated protein regime, the color producing nanostructures are created here. So that is actually when the cell has already died. So this color producing structure, what we think actually for these two different types, they are coming from the phase separation of protein and water. So the left one is called spin nodal decomposition. The right one is called the nucleation and growth. So the nucleation and growth, you can see, for example, when you open a beer bottle, you see the air bubbles start to grow in the liquid, right? That is a nucleation and growth. So here, the same thing, the water will, grow, and then after, certain size, or after they grow to certain size, it will stop, and then the water will evaporate, and then we will have air, this kind of air cavities in this protein. That is generated the color. So this kind of phase separation process is pretty, straightforward, but it's very hard to control. Because this, the feature size keep growing, so it has to stop at the right time. Otherwise, if you keep growing, the feature size and the color will be reflected, will be different, right? So we have to stop, or they have to stop this phase separation process at the right time to have very precise control. And this is very hard to do, to reproduce in the lab. And recently, my colleague, Professor Eric Dufresne's group, was able to realize this kind of phase separation in the lab through this solid state polarization to produce stable structures that has the this variation or length scale on the order of optical wavelengths. So this is really non-trivial, but it has been generated in mass quantities in nature. And but typically this phase separation worked very well, usually for soft matter, like a polymer or protein. But those soft matter usually have a relatively low refractive index, meaning they are not going to strongly scatter light or reflect light. To really enhance the color, we like to increase the refractive index contrast. And usually the organic material, like a semiconductor or some oxide, they can have higher refractive index. But we don't even know how to make this kind of structure using soft matter. To make it with hard matter is even more difficult. So we take a different approach. We try to using this kind of a template, like from this bird feather. For example, this kind of a soft matter, they have this kind of template with this very delicate structures, and then we try to infiltrate in inorganic materials like titanium dioxide that has a large refractive index, or even zinc oxide that has that has the active response or nonlinear response. And then after that, after we infiltrate the inorganic material into this bio template, we try to fire the sample at a high temperature to evaporate or to remove the this protein, or we can also remove the polymer. So this shows an inverse structure made of zinc oxide. Because zinc oxide is active material, they can add additional functionality than what we can have for this kind of passive structure made of this soft material. But I will not get into much detail to this one. But I want to say, this structure is quasi-ordered. There's actually also three-dimensional order structure we can find in nature. And here shows a few examples, and they all have a very different symmetry. This is a single gyroid, single diamond, and also this is called a simple cubic. They are very, this is very difficult, and the period is on the order of optical wavelengths. So it's about 100 nanometer. So it's very small, but they are able to produce all this sophisticated structure, in nature. And we don't know how to do it. And we don't even know how they do it. So we really have to learn from them. It seems that they are using a different approach than what we usually do. So typically what we do is that in the lab, we try to make periodic structures. We first try to synthesize those building blocks like spheres of same size spheres. Then we try to assemble them, self-assemble to form periodic structures. But we only can get a few different, a limited, right now we can only get a face center cubic from this kind of self-assembly. But in nature, they have all these kind of structures are created. So they are using a different strategy than what we're doing. So let me give you one example. They seem to do a direct self-assembly of this single gyroid photonic crystal structure. So here shows an example of this butterfly. You can see this, this kind of a green color on the, there. And this actually, if we see the scale, we see this scale here. You can see it is a green color because it reflects the green light. And here is an electron microscope image. You can see this kind of a very beautiful three-dimensional periodic structure of gyroid. So the question is how those structures are created. So it seems like what they did do is that they start with this called a lipid bilayer film, and then they fold it. They fold it to form a double gyroid structure, and then a protein called a chitin was deposited on the actual cellular face. And when the cell dies, this membrane will be replaced by air, and that leaves us the single gyroid. So you see, this actually is pretty smart, method, because we know the double gyroid is easy to assemble, through the self-assembly. But a single gyroid structure, you have a superior optical properties. So how you can make a single gyroid? We start with a double gyroid because it's easy to do a self-assembly. And then after that, remove one of the two a single gyroid, and then we left with only single gyroid structure. And that is actually how nature makes this kind of really three-dimensional periodic structures. So that really means we have a lot to learn from nature, how to make this kind of really sophisticated optical, nanostructures. So this is the first part. As I said, we still don't know a lot of things we don't know, but I want to go to the second one is how the structure color evolved in nature. So we know that actually we know structure color is very popular in nature. Many animal species using the structure color, but how they evolve, how they respond to the external pressure. So here, to study that, we study one butterfly, genus called the bicyclus. And this one, right now, they have the common ancestor, but now they have about more than 80 species. And they are living in different environments. So among all these 80 species, most of them showing in the middle here, they are, they have this like a brown, wing, right? They're like really a brown color. We don't see any colors, but we see like two species actually develop this kind of violet, band on their wings. Now the question is, why they evolve differently, right? To one has color, one doesn't have any color. So what happens there? And so if we try to measure optical, reflection spectrum from those, wings here, we see that actually for these brown ones, they do have a reflection peak, but it is in the ultraviolet regime, so we cannot see it. Okay, and but for those two species which show violet color, they actually the peak is shifted to a longer wavelength. That's why we can see this color. So in other words, for this different species, the reflection peak moved. So that's give us different colors. Some color we can see, some color we cannot see it. So now we try to say, we don't know why they evolve, under the natural selection. So now let's try to do experiments of artificial selection. Let's try to, give some pressure to a lab model butterfly. For example, like this one here. This has a brown, wing. We try to see whether they can become, the wing color will change to violet. We try to mimic the natural pressure to do that. So how we do it? This is this bicyclus aninana, and at the same location on the butterfly wing, we try to measure the reflection for each butterfly in one generation. There are many of them there, just in one generation. This is done by my colleague, Antonia Montero. She raised all these butterflies, and then we try to measure the reflection from this part, and then we see in one generation. We see the reflection peak actually has some, variation in their wavelengths. This is just a natural fluctuation, right? So then for this generation, we select only those, like the red ones has a longer, wavelengths. The reflection peak is at a longer wavelength. So we select those and then let them reproduce. And then for the next generation, we do the same thing again. We measure the reflection spectrum, only keep those, the reflection peak is at a longer wavelength. So now after, a few generations, we see this really we can see the color now. And actually we see this reflection peak, we're really shifting, to a longer wavelength, with, from one generation to another one for both male and female. So you can clearly see they're moving. They're moving pretty fast, by the way. And so if we see the scale, the ground scale on the butterfly wing, this is the first generation. This is the sixth generation of the artificial selection, which we did. We can clearly see the color now. And this basically showing this, like a part, we see many scales, they all become blue here now. So that means we can doing this kind of evolution in the lab by adding the pressure to make the structure color evolve quickly to a different color. So how could this happen, right? And so if we see, this is a electron microscope image of the butterfly, the scale. So the scale has, has this, this structure. There's an upper lamina, which has a lot of open windows, and there's a lower lamina, and that is actually, it is a thin solid film here. And this color is actually generated by thin film interference, as I mentioned earlier. The light going through these openings from the upper, layer, then they can be reflected from the, the top and the bottom surface of this, lower lamina, and then only at a certain wavelength the reflected light will interfere constructively to give this color. Right now when this when this film, this thin film is getting thicker, the color that will be reflected will shift to longer wavelengths. Okay, so that's what we see. Actually, from this ground scale, if we see the first generation shown by this orange bar, and the last generation shown by this a blue bar here, you see that they're actually, the size are quite, they have significant difference in the thickness of this lower lamina. And that leads to the change of this reflection peak. The reflection peak wavelength is shifted to longer wavelengths. That's why we see the violet color now. Actually, this thickness change is only change about 50 nanometer. That seems as very small amount, right? But it's actually, it is a lot, because the thin film itself is about a little bit more than 100 nanometer. So therefore, the wavelengths can be shifted about 100 nanometer. That can really change the color a lot. So that means for this kind of structure color, right? In order to get it evolved, what we need to do is just to try to change the, the feature size a little bit. By changing the feature size a little bit, then the color will change. And this is much easier to do compared to pigment color, which I mentioned earlier. Pigment color is really by absorption, wavelength dependent absorption. If you want a different color, you need a different pigment. Then you need a different food, a different chemical reaction path. So that is much more difficult to evolve. But here for structure color, you have the same materials, same proteins. You just change it, the size a little bit, we can change the color. That's why the structure color can evolve very quickly and respond very quickly to the external pressure. So then, as I mentioned, there's two species already evolved in nature to have this violet color. So they actually generated by the same method as we did in the lab. Is that they also have the similar structures, and this color is generated by the thin film interference from the lower lamina, which turns out to be thicker than the other species. Because for those two species, the lower lamina is thicker. The thin film interference will make the the reflection peak at a longer wavelength. That's why we can see the color. So this is basically for very simple structures that how it evolves. That's just a thin layer. And now actually I showed you all this kind of three-dimensional periodic structure, very sophisticated structure can also be created in nature. They also evolve. They evolve actually they from ordered to from disordered to ordered structure. So here it is work done by my colleague Vinod, Sarah Nathan, and also Rick Prune and Eric Dufan. They show that this kind of single gyroid three-dimensional photonic crystal structure, which I showed you in the bird feathers, they actually evolved from this quasi-ordered channel tap, this kind of structures. So, so this is really, there's a lot of things we can learn from nature, how this kind of structure is really, evolved, how they, can generate a novel, color from the structure change. So finally, let me summarize my talk. I show you that actually we can have this, basically I show you all these color producing nanostructures that have been widely used in nature, and they just seems to be able to be created in mass quantity, at a room temperature, and with really a precise control of the scale. And we still try to understand how they are generated, and we also try to mimic them. So I show you one example of this kind of self-assembly of this biomimetic color films that give you isotropic color. I also discuss at the end how this color producing nanostructures evolved in nature and how we can learn from that too. So as I said, all this work was done by an interdisciplinary team with people, from different, department. Let me acknowledge Agri Fan, Shinadon or Suji, and also Corey O'Hearn, from, mechanical engineering and material science department, and Simon Mockery from physics department. We also work with Pietro and Lynn Reagan in molecular biology and biochemistry, and Rick Prum and Antonia Montero in evolution biology, and also my colleague, Professor Doug Stone in optics. So there's a lot of, postdoc students are involved in this kind of, collective research program. I'm only going to list a few of them, which have actually, they have done the work which I showed you today. This is the list of list of people in my group. This is actually from Antonia Montero and Rick Prum, and also Eric's team, and also Corey's former student. Finally, I'd like to thank you for your attention.
Let's thank Huy Cow for this thought-provoking presentation. I would like at this point to introduce the panelists who will help us kickstart the Q&A session. So we have here with us today Wendell Hill, who will be chairing this part of the program, Raz Roy, very good, Avik Tud, who is our new hire, starting in January. He's here with us today from Stanford. Wendell and Raz are here with me in college, not in College Park, but in the Washington, DC area, I think. And I think, Wendell, the floor is yours.
Hey, thank you. So let me first thank you so much for such a fascinating talk. I learned so much about the feathers and scattering and everything. So that was really, really fantastic. I appreciate that.
Thank you.
So we're going to go into the question and answer period. And there are several ways that people can ask questions, either through the chat or the question and answer. And I see there are several already. But I'd like to start with our panel to get their impressions and their questions and their thoughts. And then we will go to some of the questions that are coming in over the line. So, well, let's go with the senior member first, Raj.
Thank you so much for this absolutely glorious talk and tracing the history of structural color and different mechanisms from pigments to interference and all kinds of different fascinating elements that come in. But I was most fascinated by the beautiful quality and consistency in nature in replicating these things from bird to bird, from species to species, and how astonishing the beauty of all these different creations is.
Mm-hmm.
So I was really curious by one of the things that you mentioned, that there is an ultraviolet peak in the reflection from these butterflies, wings that you showed. And, we can't see that because we don't see in the ultraviolet, but butterflies do, apparently.
Exactly. Exactly. They're using this for communications, actually.
This was my question to you. Yes. Okay.
Yeah. They're using this for communications, and they're also using this not only for communication with themselves, but also with their, say for the butterfly, right? They also have their enemies. So we actually try to see. I don't have time to show you how the color is used in nature. For example, one of the butterflies, what we find out is that they have this kind of eye pod, right, which is look like a white to us, right? But they actually reflecting, they actually has a color, I should say. So they basically, when they see, okay, so maybe I'll just try to share my screen again. I think that for this, So what happens for this one is that this kind of, they try to using this to distract predator. Because if they have some, things here, when they flash it, then the predator will, for example, if they see they can flash it, and when they flash to the back, then this predator will, jump to the back, then they can leave. And then we did experiments, which is we painted, we painted the butterfly wings. And then so we remove this kind of color, and the butterfly this is ultraviolet, still ultraviolet, we cannot see it, but we can paint it. And then when this the predator came, in the lab, and then this butterfly tried to flash again. Of course, there's no this color to really attract the predator, mantis. So the mantis was really just attack the body of the butterfly.
Oh boy.
Yeah. So it's very fascinating how they're using this kind of color, not only communicating between themselves, but also try to protect themselves.
Interspecies communication and protection. Yes. Thank you so much. That was a question I really was wanting to ask you. Thank you.
Thanks, Raj. Well, I'm going to use my prerogative as chair to have a follow-up question to that. Is it possible, or do you know of examples where these colors can change in real time? I mean, can you do something to their structure in real time to change the either the absorption or the scattering or the interference?
Yes, it can. So this is a video which I used to have, but I kind of remove it because the thing. So let me just show you one thing really quick, how this color can change. This is not my work. I have to say this. Can you see my screen now or not? I have not shared my screen yet. Okay, hold on. Let me share my screen. This is not my work. This is work of a Weizmann group, but I'm going to show it to you. This is actually the team. So let me. Okay. Hold on. So this is okay. Hold on. Why I don't get into the display? Hold on. Display the slideshow. Right. So this is a kind of a very small animal they find in the Mediterranean Sea, right? So you can see this very nice color, right? So if I start this thing, then they try to change they start to illuminate it. This is in the deep sea, so they are very colorful. Now, if you take it out, you have the sunlight to do it. Now you see it's very quickly changed to no color. You see the front part, this part, and they can change in real time. They can really change in real time to adapt themselves to the environment.
Fascinating. Thank you.
Yeah.
Fascinating. So, Avik, do you have any comments?
Yep. Hello, Professor Shao. That was a wonderful talk, and I really learned a lot, as Rajrai also said. I was thinking of this in a more, let's say, physicsy context. This interdisciplinary topic that you're exploring. So you mentioned coherent backscattering in one of your slides in the first half. And since these structures have short range order, they're quasi-periodic or quasi-random, whichever we want to talk about it, is there any connection to, let's say, weak localization in Anderson localization kind of models for light? Because that could also produce some of these effects or
Yeah, that's a very good question. Actually, indeed, this kind of thing you can, as I said, Anderson localization can happen also near the band edges. You have, some, periodic structure with some, disorders and near the edges. And this short range order structure could have that. But the thing is, in nature, it is difficult because the index contrast is too low. Because, for protein index is 1.5 and then to 1. But we can try to infiltrate high index material, right? Like silicon or other things into this kind of structures. Then we can try to use this to study maybe, as you said, this kind of Anderson localization in this quasi-periodic structure. And people have already studied this called hyper-uniform structure. I don't know whether you heard about that before. Is that also this kind of, there's a lot of studies about that, but as I said, you really need a higher enough index contrast to enhance the scattering to really get into the localization regime. Here, this just try to generate the color. Yeah. But yes, that's possible.
right, thank you. That makes a lot of sense.
So great. That's a good transition into one of the questions that came in on the question and answer from Tian Yu Li. He asked the question, the following. He says that Raman scattering is caused by polarizability change in the particle, which does not necessarily need interference. Could you specify in more detail how Raman scattering can play a role in ordered structure and determine the color?
Okay, so I think that is maybe I caused a misunderstanding. Raman scattering is actually invented by Raman. He got a Nobel Prize for that. But this color, this light scattering to produce the color is not Raman scattering. Raman scattering is an inelastic scattering, meaning that the scattered light and the incident light has slightly different wavelengths. Mm-hmm. Here it is the same wavelengths, the backscattered. Raman just have this hobby of really collecting a lot of bird feathers, study how their colors, their colors in it. So this, yes, so that's how he studied this to see this is not Raman scattering. I have to clarify. This is an elastic scattering, and coming from this kind of quasi-ordered structure, the elastic scattering can have constant interference for certain wavelengths. Not for Raman scattering, yeah.
Mm-hmm. Good. Well, does the audience have any further questions? I know Ted Einstein asked a question, but he also then said that your answer to Raj was basically answered his question. Ted, if you want me to ask the question, please either raise your hand or say something more. Do we have any more questions? Constantina, do you have
Yes, I would like to ask a question. Could you share with us a research dream, a research aspiration that you have in connection to this topic and its potential impact to society, beauty, technology?
Yeah, I think that really my dream is to really be able to generate all these sophisticated three-dimensional, photonic optical structures with the mass quantities, at the room temperatures and with well controlled. Because if we can do that, we can, using this, for many things. I said for coating, even for solar cell, how you can trap light, you can using this kind of quasi-ordered, this kind of, scattering structure to trap light. And so there's many, of course, my dream is someday we can do the things that we, the nature can do, meaning that we can really learn from them enough. We can make all these sophisticated three-dimensional, complicated structures. But that's not it. We not only want to learn from nature, we want to outperform it. So of course, so we have, even we don't know how to make those delicate structure, but at least we have many materials, right? In nature, they're only using protein, the index, only protein. They're using the protein, which is index 1.5. We can have many materials has many, higher index, different index. We have material has a nonlinear, response. We have material has active response. We can make a laser out of it. So if we can learn how they create those kind of structures, and we can combine with different materials, then we can do many things. So we maybe will be outperform nature.
Oh, wonderful. This is a big dream. Yes. And one more question. It seems to me, speaking as mathematician, applied mathematician, there is a lot of room for applied mathematics in this topic.
Yes.
And I was surprised because I didn't see any applied mathematician in your group.
Yeah, we try to actually, for this, I didn't list it here, but we are, actually my colleague was talking with somebody. It's because you see this infolding, as I said, this kind of membrane, when they infold it, is highly non-trivial how they do this kind of folding, and how they control the curvatures, and how they make this double gyro structures, and how they can remove one of them. There's a lot of really this kind of spatial symmetry. Yeah, there's a lot of things in there.
In our institute, we have many applied mathematicians that will be eager to collaborate with you. This is just one more remark about this.
I'm introducing my colleagues because, I have also a lot of colleagues here who would love to do this because, as I said, we're not mathematicians, we don't know this, but it'd be great to have this collaboration.
Thank you.
I was fascinated by how the cells change in time. And if I understood you correctly, you said it's basically the dead cells that have this really brilliant color.
Yeah.
And then, of course, they evolve in time. So I'm going to go back to time again. So if you try to mimic this in artificially, how would you do that? I mean, where are you, or where is this the field in trying to mimic this? I know you show the picture of the car and things of that sort, but
okay, then I'll try to show you another video if I can get it. So we are trying to make this tunable. Well, it's not we. That does not mean me, meaning the community, right? Actually, let me show you one work done by a different group. Let me try to share my screen again. Okay, and so this is basically this isotropic color. So this is a Korean group. They make okay. Can you see my stuff right now? Okay.
Yes.
Okay. So now they make this kind of a color because usually, usually if you want to do this ones here, you know, for display, you don't want the color to change with angles, right? Because you don't want to see like see a tree look green in one angle and then look blue in a different angle, right? So that's why the isotropic color is very useful. So now so what they do, they make these particles in some solutions. And then they apply this, you know, like a transparent, the in between two transparent electrode. When they apply this voltage, they can changing the spacing between those things, between the spheres. Then they can changing the color that's being reflected. So show you this. This is a movie from their papers. You see the color is changing from. This is in real time. By applying the voltage, you can change the spacing between those, you know, spheres. Then you can changing, you know, which, you know, wavelengths they'll reflect, you know, by the constructed interference.
It's fascinating. We have a question from the audience from Stephen Ferber. Can you imagine why iridescence evolved? Just more identification of species, specific species like color in general. Also, didn't this begin with dinosaurs?
Yes, it does. I mean, actually, so actually, yeah, the non-iridescent color will be used for recognition, right? You recognize because you want to see the birds the same color in all angles in there, right? So it's for the like a communication. Yeah, the color actually start from dinosaur. Actually, my colleague Rick Proom, they have been studying from the fossils to study the color of from the dinosaur. You know, so there's a lot of studies of this kind of a fossil, and not only like a beetle I showed you, also from, you know, like a dinosaur, another, you know, a species. Indeed, the structure color has a very, very long history.
Okay, and you had a follow-up about octopus and chameleons.
Oh, yeah. Sure, exactly. Those can really also change very quickly. You will see this, you know, amazing videos, which how they can, you know, quickly adapt to the environment. So there's all these kind of things happens in nature, and again, we have to learn from them how to do this in a very efficient way, you know, and very fast and also energy efficient.
Very good.
In other words, from one color to another color, what is the shortest distance, right? If you know, to go from one to another one. Yeah.
That's just fascinating. That's
Mm-hmm.
wonderful. Well, I don't see any more questions. Does anybody have any last comments?
Can I ask one more question if there's some time? Yeah.
Sure.
So this is about the last part of your talk where you talk about artificial selection.
Yeah.
But in photonics, as we know, inverse design has become quite popular these days.
Yes.
So is there any scope for using inverse design to help mimic nature or even outperform some of the metrics that you were mentioning earlier, to build structure that outperform nature's performance instead of using, let's say, population selection or artificial selection pressures?
Absolutely. I think that this one, you know, this experiment we're doing there, we just want to, you know, mimic in the nature. If you have external pressure, how the thing evolves, right? But this is actually not a trivial experiment, because my colleague Antonia has to raise all these butterflies and from one generation to another, you know. But this is, but I think indeed, you know, this kind of artificial intelligence and all this kind of inverse design could help to really optimize this kind of photonic structures. Indeed. Yeah, that's a good direction.
Well, there's another question on follow up on the dinosaur question from Theo Gifford. For the fossils that with strong colorization, is there a way to trace the color back more accurately compared to dinosaur coloration? For example, with sound, which sounded very much like the work in progress. So can you do more with fossils?
Yeah, I think there are, I have colleagues here at Yale, actually I did not list them here in geology. They were really studying extensively on the fossils, on this kind of colors. They try to, analyze the structures, then try to really figure out, as I said, 40 million years ago, how the color looked like for those beetles, for those, dinosaurs, or for those things here. And also try to understand what the use of those colors many, many, many years ago. Yeah. This is still in progress. Yeah, but I think there are some papers. I think my colleague Rick Prune has a paper on this dinosaur color. I'm not on that paper, but I think there's definitely more. There are publications on that. Yeah.
Okay, Ferber has one more question on cloaking and how this might be relevant to cloaking technology.
Cloaking is if I understand correctly, is more to as you said, hide yourself by making the light going around it. I haven't seen that. Well, I have very limited knowledge for this biology. I haven't seen that in nature for this cloaking. Maybe it's there. Right now, for nature, when they try to hide themselves, they just try to develop the color to mimic the environment. When the environment color changes, they try to change to follow it. So they're not trying to really have the light bypass it. So that one we have not seen yet in nature. Well, at least I have not seen that. Yeah.
Okay. Well, Konstantina?
Well, what an
back to you.
enthralling session that was. I would like to once again thank our distinguished speaker, Huy Cow, the generosity of the Pi family for making this lecture series possible, the panelists, and the general public for making this a memorable occasion. So if there is no other questions or comments, Huy, do you want to add something?
No, I think this is really a great experience for me. I'm really appreciative of all the questions, from both panelists and also from audience. I think I hope that to just give you an overview that there's a lot of things can be done. I hope this will inspire some of you to do this, or
Very
maybe
good.
there's a lot of questions and there's also very fascinating. So if you have any questions in the future, please feel free to send me an email. I'll be happy. If I cannot answer your question, I'll try to, direct your, to my colleagues, my collaborators at Yale.
Very nice.
Thank you very much.
Thank you so much.
Thank you so much.
Thank you.
This
Thank you.
concludes the 2021 Dr. Shih-I Pai lecture. Thank you
Thank
all of you
you.
for being here.
Thank you. Thank you.
Thank you. Bye-bye.
Bye-bye.
Bye.